am going to officially now dive into our newest chapter, which is talking about the allyl group or allylic groups. And this is definitely going to bring in those concepts of the carbocation and the substitution especially. So just keep that right here in your head. Okay, what is an allylic group or an allyl carbon? Essentially, this is a special scenario, carbon scenario, in which we have formed a extended pi system. I'm going to stop just a second and talk about these more, but what is a pi system? What do we usually associate a pi system with? Pi bonds, what's the other word for that? Overlapping, or if we see them just a singular one, we think of a double bond, right? That's in a triple bond, we also have pi bonds that they're doubled up, right? So a pi system that has been extended is a scenario where the electrons that are in those pi bonds, normally what you would see in a double bond or a triple bond, exist in a neighboring carbon because of a addition or removal of electrons, altering its HOMO and LUMO system. Essentially, there are three scenarios where this happens. If you have a carbon that is a cation, positive charge, next to a double bond, so notice it's next to a double bond, or you have a carbon that has a radical on it, a single electron, next to a double bond, or you have a carbon that actually has an extra pair of electrons. It has a negative charge next to a double bond. Notice that all of these require it to be the direct neighbor of a double bond. That's because it is utilizing the pi system of the double bond to extend the electron system over those three carbons, essentially. So its interaction is specific to being next to a double bond. This scenario, any of these three scenarios, creates an allylic system. We call the carbon that is charged, the one that is not intimately involved in the double bond, but next to it, we call that often the allylic carbon. Sometimes that word is used to just describe a carbon next to a double bond because it has the potential to make one of these allylic systems. So you'll sometimes see that get used, and it's a bit confusing, I know, but people will refer to, oh, it's just a carbon next to a double bond. It's an allylic carbon. But it hasn't formed one of these systems in which the pi system is throughout the three carbons. We're going to see more of what that means, but essentially, when you get one of these scenarios going, resonance can occur through all three of those carbons. Electrons get shared through the pi bonds of all three of those carbons, and they are in resonance. What does that mean? It means that you can get some funky things going on in reactions because now the electrons are shared. So they're not just hanging out in one place, they're shared throughout the three carbons. And so when reactions are occurring, there's equal potential for that reaction to occur now on the three carbons because they have this shared system. Again, we'll see more what that looks like, but generally speaking, that's what's so special about these allylic systems. Again, when you get one of these scenarios, you then have resonance across the three carbons, and it will lead to some changing reaction patterns. Now, these guys don't just like exist on their own. Just like when we were talking about the carbocation, right? It It doesn't just like to hang out as that. So we're not just like going around with an allyl cation or an allylic radical just being there on its own. Often during a reaction, first, one of these is formed. So there's a step process where you form one of these, and then some interesting chemistry happens, okay? That's why I said often you'll hear just a carbon sitting next to a double bond referred to as an allylic carbon because it has the potential to become one of these systems. Okay. Okay, so let's talk a little bit more about conjugation, which was brought up. That's why I was saying you guys are hitting it with resonance and conjugation. And I was like, oh, we're about to get there. So let's talk about conjugation and conjugation of pi systems. Conjugation can occur. This is with double bonds specifically. And in this case, with double bonds next to another pi system, but it can also occur in alternating double bonds. So essentially, double bonds affect the properties of attached groups that contain unhybridized p orbitals or pi bonds. And if you have 3 or more adjacent p orbitals, we get what's called a conjugated pi system. So this is the smallest pi system you can have, an allylic system, because it's 3, smallest pi system. But you can have conjugated systems that are even bigger if you have a lot of double bonds next to each other, for example, because then you'll get a string of p orbitals, these pi bonds, you'll get a string of them all in a row, and electrons can move through all of those orbitals. So essentially, 3 or more p orbitals that are unhybridized. So if they're involved in these double bonds, or if they're involved in, like I just showed you, one of those scenarios, they count, and electrons can move through them. This is a critical scenario. Conjugated pi systems is critical for a lot of things, actually also in biology. So I will quickly note, actually, many of the molecules, especially involved in your eyes and seeing, have these conjugated pi systems, and allowing the light waves to hit them and move the electrons through them specifically registers certain colors. So it's critical in biology. Often many things that are organic dyes, so dyes that come from organic compounds instead of metals. Just a quick note, metals, very pretty usually. They have colored systems. Generally speaking, organic molecules are really boring. They tend to be like clear and white and tan, except if they get one of these systems, these conjugated pi systems, because now they got electrons that can move through their systems, and that turns into scenarios where you get essentially pretty colors. So organic dyes, and if you see anything colored in nature, like, I mean, flowers and in flowers, pigments in anything, they have one of these systems, conjugated systems. Okay, so again, this is the simplest of a conjugated system. Like I said, you can refer to the carbon next to a double bond as an allylic carbon. And these scenarios where we have the allylic carbon results in resonance, as I said. So meaning that the electrons are shared over all 3 carbons. And what that kind of boils down to is that truly this is a realistic scenario that you're getting. So here's an allylic system right here. You can see there are 3 carbons. These 2 right here are part of a double bond, and this is a carbocation, has a positive charge. But realistically, this is in resonance, meaning that the positive charge can essentially flip over to this carbon on the other end, and the double bond can now flip to these 2 carbons. and they're resonating between those two states. So often we draw it like I've highlighted on the end, just to say that there is not one state or the other. These are flipping between the two states back and forth. So they are resonance stabilized. This is, yes. Are taught to, no, they're not. So they actually have they're not a true resonance, why we call them tautomerization. They're not a true resonance because there is movement of bonds in those. So they're like a resonance adjacent scenario. That happens a lot in biology. We have this like keto-enol tautomerization, especially that goes on in sugars. And there is a movement of a hydrogen that happens in it, which is why it's not like really a true resonance. There is kind of a resonance that happens with it. But if you want to talk more about that, we can talk more about it. Definitely like in biochemistry, something that gets brought up. Okay, so resonating between these two forms, notice that essentially the positive charge has flipped to either end with that double bond going to each of the other end. This scenario can happen for all of those three scenarios I brought up, right? Remember that allylic systems can happen if you have a negative charge or a radical, not just this cation that I'm showing an example of. So what does that look like? As I was kind of describing, here are the orbitals. This is what is essentially the double bond. It's being shown as the pi orbitals that already exist. Double bonds have these pi orbitals here, these p orbitals that are already overlapping with each other. And when you create one of the scenarios that I gave, either with the cation, the anion, or the radical, you create this now unhybridized p orbital, and essentially they can all now overlap. That's how you get this resonance. That's also what's happening in conjugation. You just get a continuous elongation of this in a conjugated system. It's all about the p orbitals. Hey, careful where I pause in that sentence. Okay, so told you I was going to bring it up. SN1 and SN2 reactions involving allylic halides. I did note to you that these allylic systems don't just like exist, they have to be made. One of the very common ways that they are created is if you happen to be doing a substitution reaction, particularly if you happen to be doing an SN1 reaction. So, and the site where you're doing the reaction, the substitution, is on a carbon that's next to a double bond. So here's an example, right? This carbon right here, it's a tertiary carbon. It has a chlorine on it. Chlorine is a good leaving group. And it goes through its SN1 reactions, getting ready to substitute out that chlorine. In the meantime, remember, it forms this. It forms a carbocation at the site where the chlorine used to be. And what do we have? Now we just happen to have a carbocation that is next to a double bond. So SN1 reactions, starting off on an SN1 reaction, you often can create these allylic systems if it is happening on a allylic carbon, a carbon that's next to a double bond. Okay. The thing about this is if this happens, then in the middle of your reaction, you're going to get resonance, meaning that this molecule also exists. So that positive charge can now flip all the way to the end, switch with the double bond. And that means you actually have equal chances that you do a reaction, a substitution on either one of these sites. Now, one site might be favored over the other because of it being more stabilized. But for example, that's true here. One of these sites is more stable than the other. But the point is, this can happen, this resonance can occur, and now you have wacky chemistry. Can anyone tell me which one is the more favored cation that will accept the new group? Yeah, so which one of these two versions that can now exist because we have an allylic system, which one of these two versions is actually the version that's more likely to react? The one on the right? Why do you guys say the one on the right? Yeah, left one because it's more stabilized by its neighboring carbons. Carbocation, more stable in this form. And so thus it is more likely to, oh yeah, it's more likely to exist in that form. Even though both of these resonances can happen now, we've opened it up to both of them can happen. The left one is more stable, more likely to stay in that scenario because it has its neighboring carbon buddies. It's more stabilized there. And so your substitution will still likely take place on that carbon, which just so happens to be the one that it started on in this scenario. But because it has more carbon neighbors.
So is that another way of saying it spends more time in that state?
That's exactly what that means. It's spending more time in that state. But the point here is when you have a scenario, when you're doing one of these SN1 reactions and you form a carbocation, if it is next to a double bond, just remember now you've opened up the potential to this resonance. That means that even though in this particular example, the starting one still is the more likely place of reaction, this other resonance form is still open to potential reaction. And you can get substitution now happening here on that carbocation. Something that is interesting though is that when you have these allylic systems, in comparison to just a normal alkane substitution that doesn't have a double bond next to it, these reactions happen faster. And that's because the carbocation is not only now stabilized by its carbon buddies, it's stabilized through resonance. So just having this resonance occurring, one, makes for some wacky chemistry, but two, makes the reaction occur faster because of stability. And like I said, that particular example now notes that there are two products that could be formed. You could substitute out your chlorine, and in this example that they're showing at the bottom, they're adding in the new incoming group is an alcohol. So you could add an alcohol essentially right here, or you could add the alcohol on the end right here. Notice, as I stated, both products occur, but which one occurs in majority? The first one, right? The one that you guys already pointed out on the left, because that's the more stable scenario. And we can see in this slide, they've listed the actual percents of each of these they got, and it's definitely skewed heavily towards the other one, right? 85% versus 15%, yes.
Can you explain why the lack of double bond makes it slower, like in the last slide?
Yeah, so this is a scenario where we do not have any allylic system. This just to be clear, this SN1 reaction is still going to happen at a decent rate. It's not like this is a bad scenario for SN1. It has a tertiary carbocation. It's a good SN1 reaction. It just so happens that if you happened to be in a scenario where, like I have here, you have a double bond next door to that carbocation, the double bond and the carbocation can do resonance, as shown here. And the resonance stabilizes the charge. So having the ability to do this resonance helps stabilize the carbocation, which, remember what I said about SN1 reactions and their carbocations, the crucial thing is stabilizing those carbocations, right? That's the crucial point we have to get through. So anything that helps stabilize them makes the reaction faster. And if you have resonance there, it stabilizes it more. You're welcome. If it doesn't have any extra carbons, sorry, repeat it.
The last slide where the bottom one,
Yes.
it doesn't get the carbon, or you think it doesn't have a double bond. Were you also saying before that I don't know what you're referencing one, but it doesn't have a double bond.
So what I'm referencing is that the difference between this and this scenario is that the top scenario can do resonance because of the double bond next door, and the bottom scenario cannot. And just because of that, this top reaction has a faster rate actually than the bottom reaction. They're similar starting scenarios. They're obviously not identical, but similar to just compare the rate that it happens. All right. So we have some carbocations here. This is a practice problem. I want you guys to rate the carbocations in order of increasing stability. So this is least stable carbocation to most stable. So can you guys point out, first of all, the least stable carbocation here? Does anyone have an idea? Least stable. I'm just gonna, for a second, I wanna, this one, if you can't see very well, number 3, this is CH3 right here, which actually means that, that's right. So it's really like this. And there's a carbon with 3 carbons on it. And then there's this CH. Oh, yeah.
This may sound like a stupid question, but should we be able to?
No, I wrote that wrong. Sorry. Go ahead.
Should we be able to tell the stability just from this written formula? Like, I feel like I have to draw it.
From that formula, you mean?
Right, we should be able to tell just by
So I know that you are not alone in the sense that a lot of people struggle seeing these formulas. And I think if you can at least practice taking that formula and drawing it out, then do that if that help you. Because I agree that sometimes drawing it is the better scenario. So just seeing the formula, I know is a confusing scenario. Personally, and people who have had me before on my tests can attest that I like to have everything in the drawn out form because it's clear and not in the condensed form. But this condensed form pops up a lot in the text. So I put it in here so you guys are used to seeing it.
Thank you.
Yes. So you are right in this. This is a tricky scenario, right? Because it looks like it is a carbocation that's tertiary, but it's actually on a primary carbon. Yeah. So this number 3, this carbon right here is actually a primary carbocation. It's right next to a group. This carbon, because remember, we're talking about this guy right here, right? Now, if the positive charge was here, it would be tertiary, but it's not there. It's on the one on the end. So it was tricky. And why I think that it was good to draw it out in that scenario. Because if you saw that quickly, you might be like, oh, there's three methyl groups right next to it. Looks good. So in this case, the least stable is 3. Yeah. Least stable is 3. Okay. It's okay. You just said it backwards. It's fine. I knew where your head was. It's cool. Least 3. Least stable. What is the next least stable? Next one up, 1, right? And then the most stable, 2. 2 is like 1 in a position where it would be a secondary carbocation, but it has its resonance stability. It has its double bond next door. Remember, it has to be a double bond that is its neighbor, right? If that double bond was 1 more carbon over, you're not getting any of the benefits of the resonance. And so that double bond is like not a player in the case that I just gave you. Here it is, right? Just want to be clear on that. These allylic systems only ever occur, right, when it's a carbon next to a double bond. How do I draw number 1? This is just 3 carbons. So like this, and the positive charge is in the middle on that middle carbon.
To clarify, so 2 is the most stable because it's in 1 is next because it's
You're absolutely right. Got it. This was more so to get you guys not only remembering that, like I reviewed in the beginning here, that tertiary, then the secondary, then the primary, that's stability going towards the carbocation. But now also remembering that if you have that allylic system, that adds stability, right? So it's like a plus to any of those scenarios.
So
It's okay.
7 carbon, 7 hydrogen. So why would it, yeah, so why would it be 8? Like it'll be 3, 3, and then something for number 1. Would it be 2?
So it would if it wasn't a carbocation. Remember that these carbocations, this is a scenario where a carbon only has 3 attachments and a positive charge because its 4th attachment was taken away. So right now, that carbon right in the middle, it has an attachment going to a carbon, an attachment going to a carbon, and a 3rd attachment going to a hydrogen. Its 4th one has been taken away, and it has a positive charge. Actually, all of these scenarios are like that. Each carbon only has 3 bonds to it. So that's why if it was neutral, it would have 2 hydrogens. I will go here for a sec. Could the 3rd one methyl shift into being more stable? That's a great question. Let's look at it. So you're saying, could this shift over, this whole methyl group shift here and switch places, which would result in this, right? And now that would be a tertiary. So yes, it could. Great eyes. There was a question back here. Okay, I'm sorry. So just to be clear for those, if you guys missed it, what the methyl shift can only ever happen if it's a neighbor. And I took a whole methyl group, that was this guy, and I switched places with the ion part, the positive charge. So that whole guy is here now, where the positive charge used to be. And the positive charge is where it used to be. Swap. Yes. For number 2, you mean? Yeah, that's it. Yes. If there was another carbon between them, that double bond would be not doing anything, and you would not even consider it as adding any more stability. You would just consider the fact that it was a secondary carbon cation. Good questions, guys. All right, what about if you do an SN2 reaction on one of these allylic carbons? So you start off with a group that is next to a double bond and you do an SN2 reaction. What do you guys think? If you do an SN2 reaction, right? So I'm going to draw an example similar to what we had, right? So you're going to do a substitution reaction on this molecule, okay? So part of that means that however the mechanism, we're going to get rid of this chlorine and we're going to bring in a new group. Let's just say for the sake of an example, I'm bringing in a OH group, right? Remember that this can happen through 2 different mechanisms. We just talked about what happens when you do it through an SN1 mechanism. SN1s form carbocations, right? What about an SN2 reaction? What do you guys think? This is goes in one, is there ever a carbocation formed? No. Is there ever an allylic system formed? So no, because remember the requirements of this allylic system? You have to have a positive charge next to a double bond, a negative charge next to a double bond, or a radical next to a double bond. Does an SN2 reaction ever make a carbocation? No. It doesn't do any of these other things either, does it? No, it doesn't put a radical there. It doesn't put the negative charge there. It doesn't form an allylic system. So there is never resonance occurring or an allylic, there is never this allylic conjugation going on. Now, what on the slide says, which is true, is that the process of this happening is still somewhat stabilized by that double bond nearby, even though there's never a true allylic system formed with resonance occurring. So SN2 reactions still go a little bit faster if they happen next to a double bond. That's the key takeaway here. They go faster than if there wasn't a double bond next door. But they do not have resonance, meaning for an SN2 reaction, no funky chemistry, because there's never an opportunity to now put something on a different place because there's no resonance occurring, because no allylic system was ever formed. Yes. It just, the SN2 reaction just still happens faster relative to the same scenario, but with no double bond next door. Yes.
Is this a thing where
It does. SN2 reactions do. SN1 primary, tertiary, SN2 primary. Just saying, like, so if I just reached for a pen that doesn't exist. If you had the same exact scenario like this molecule and you were doing an SN2 reaction on that molecule versus you're doing an SN2 reaction on the one on the top. The one on the top, that reaction just goes a little bit faster. There's no funky chemistry that happens. They still just do their substitution as normal. It's just that having the double bond nearby makes it faster. Really, all of the weird stuff happens with the SN1 reaction because it forms an allylic system. That was kind of just a side note on SN2. It happens a little faster, but nothing else weird goes on. Okay, so another question here. Choose the compound that yields the same carbocation as 3-chloro-1-methylcyclohexene. I'm going to stop before we choose these and draw out what the name says. So let's do a little practice taking a name to a drawing. First of all, what is this? Can anyone tell me what a cyclohexene is? Or even a cyclohex? 6 carbons that are, what's the cyclo? Ring. So let's start there. 6 carbons in a ring. And what is the ene? Not a triple. Ooh, I drew that really bad. Let me redraw that. I'm going to draw it down here. Okay. Okay. Oh, man, it's so much easier when I have my pen and touchscreen. Okay, here's my 6 carbon ring. There is a double bond in it. Ene is double bond, ine is triple bond. And does it matter where I put it? It says in this case, there's no number, meaning I assume position 1, so it doesn't matter where I start putting it. What else is in here? A methyl and a chloro. I heard mix of things. I'm going to start with the methyl. Okay, so, and it's on the where? First carbon. So I get to decide where that is right now because this ring it goes in a circle, right? So here's my methyl group. Okay, so this is 1. That means that down here is position 2 and right here is 3. So there's a chlorine here. Boy, at the bottom of the screen. Sorry, guys. Okay, here is this compound. It says we want to choose a scenario that would yield the same carbocation as this guy. So first of all, let's talk about what kind of carbocation this would. Can anyone tell me what thing on that ring would leave as a leaving group? Chlorine. Okay, we're all in agreement with that, right? If it left, then I'm just gonna erase that. If it left, then you would lose your chlorine here and get a positive charge right here, right? Have I made an allylic system in this ring down here? I did, right? I have a positive charge that is next to a double bond, meaning that this can have resonance. And what is the other form that this can take? No methyl shift, just resonance. Allylic systems have resonance. So no shifting of anything, but remember that the double bond and the charge can switch back and forth. That's what resonance is, right? They're resonating back and forth, meaning that the other form of this is the double bond here and the positive charge here. Okay. I formed an allylic system and allylic systems can resonate. And here's the 2 forms it can resonate between. That's this starting guy, just to clarify. This is a complex multiple choice question.
So the double bond switch with the positive charge.
Yep. That's the resonance that can occur in these systems. So really what this is saying is, which one of these other scenarios, if I did a substitution, I remove the chlorine and I make a carbocation, which one of these other scenarios would result in this scenario at the bottom? Or at least a form of this scenario. That's all it's saying. Anyone have an idea of what one of them? Yeah, go ahead. So this is actually a tricky scenario. It's not going to go through a substitution because why? It's on a double bond. So it won't actually do a substitution. Remember that these substitutions have to happen on single bonded or sp3 carbons. So yes. So this one can't happen. On D, if I removed this bromine, that would put a double bond here. So it would be like double bond methyl, or excuse me, positive charge methyl double bond. And this can also resonate, but does it resonate to form one of these scenarios? It doesn't actually, because of it's the positioning of where the methyl is and the charge. Do you see that? See how like now the methyl's like between the double bond and the charge? So it actually doesn't happen on D. Okay, and A, I would form a charge here right on the methyl with the double bond down here. Do I have a scenario like that? I do, and it's actually right here. Do you guys see that? This and this are the same. It's just that they're just drawn a bit different.
Would it be a good strategy to just draw all of these out?
I think so, yeah. Yeah. That would be my strategy.
Instead of just,
Yeah. Definitely in the case where it gave you the name, 100% you have to draw that out because you're not going to be able to just visualize what the resonance looks like.